Electrophoresis is the movement of colloidal particles in response to an electrical field. So let's look at that. So imagine we have a tub of water and we have some sort of voltage source. And we then have a positive electrode and a negative electrode. And we've got some colloidal particles in there. And let's suppose that we have colloidal particles with positive surface potential. So we'll draw some positive charges on the surface here. Now we know that in response to the potential field set up around each of these particles, it's going to attract an excess of counterions and a deficiency of coions. So I'm just going to draw some counterions. And we remember that I'm arbitrarily drawing a circle approximately 1 debye length away, but the excess of counterions is going to extend out into the solution. It's just going to die off exponentially. Okay, so if we think what's going to happen in response to having a positive charged plate here and a negatively charged plate here, we're going to have an electric field that's pointing to the right, from positive to negative. And we know what that's going to do to the particles. The particles are positively charged. We've got these electrical fields pointing to the right, so it's going to push these to the right. On the other hand, we've got these spheres of solvent with an excess of counterion, so they're going to be pushed in the opposite direction. These two effects don't exactly cancel though, because if we look at these larger spheres, because they're larger, they have a larger drag force on them, so they're going to move more slowly. So the net effect is still going to be a migration of particles to the right. What's the speed? The speed at which these particles are going to move is actually going to be a complicated function of the ratio of debye length to the radius of the particles. Fortunately, there's two limiting cases that we can use. For particles that are large, that is, in comparison to the size of the debye length of the solvent, we're going to use the Helmholtz-Smoluchowski equation. So going through this, we see the speed of the particle, or rather the velocity, is going to be in the same direction as the applied electric field. And if everything else here is positive. So we've got the two dielectrics, the vacuum permittivity and the dielectric constant of our solution, our zeta potential, and our viscosity. So if we have a zeta potential that's positive, then we can see our particle is going to have a velocity in the same direction as our applied electric field, as in our example. On the other hand, if this is a negative surface potential, the particle will move in the other direction. We can also see that the speed at which we move is going to be inversely proportional to our viscosity, and of course we saw that for laminar flow, viscosity and the force of drag are proportional to one another, so it makes sense that the bigger the viscosity, the slower our speed. If we have small particles, in other words, if they're small compared to the debye length of the solution that they're in, we're going to use the Huckel equation. Note that in this case, we have the exact formula as before, except that we have a numerical factor of 2/3. If the particle size is comparable to the debye length, we're in between these two cases. We can't use either limiting case. We can see that we could estimate by using a number intermediate to these two.